Hi, welcome back. In this lecture, I want to talk about a module called numexpr that we're going to use to optimize NumPy vector extraction. So this is the last optimization technique that we're going to apply to our diffusion problem code. By the end of this lecture, we will be able to describe the features and advantages of the numexpr module in Python. And also we'll be able to describe on its advantages to use NumPy with and without numexpr. So we'll see that sometimes it's advantageous, sometimes it's not. So one of the downfall of the NumPy optimization of a vector operation is that it occurs on only one operation at the time. So vectorization, we do one vectorization from one operation and then another vectorization and then another vectorization. So in some sense, we could fuse all the vectorization together, but NumPy doesn't allow us to do that. So we vectorize first expression, second expression, and the third expression. But instead, we could fuse and merge all the vectorization in just one expression. An example, for instance, is when we are doing the operation A multiplied by B plus C, where the A, B, C are a vector, and this multiplies element by element operation. So what happens? Well, first, yes, we use the vectorize, but if you just compute A multiply B elements, this completes. We store the data in a temporary vector, and when we take this vector and when we add the C through vectorization, but this is an independent vectorize operation. This is an example that we have in our diffusion code where we can see clearly how these all vectorizations are just one after the other one. What I want to describe now is a package that allows us to optimize this vector extraction. So numexpr is a module that can take an entire vector extraction and compile it into an efficient code that is optimized to cache misses and temporary space used. So especially allowing for in-place operation that we saw in the last lecture are quite important. The main reason why numexpr achieves better performance than NumPy, so numexpr is used with NumPy is to further improve the performance. So the main reason that performs better than the flat NumPy is that numexpr avoid allocating memory for intermediate results. So we take advantage of in-place operation. Also, another advantage is that the results is these results in better cache utilization and reduce the memory access in general. In addition, the expression can utilize multiple CPU cores, so this is very good for multi-core programming. If we use numexpr, we can use all cores available on our processor and take advantage of specialized instructions our CPU might support in order to get even greater speed up. It also supports OpenMP, that is a programming approach in the compiler for C and Fortran that allow us to make a code multi-threaded and use a multi-core architecture. OpenMP parallelize some extraction, typically loops. If you're interested in OpenMP, we are going to describe OpenMP features in DD2358 methods in high performance computing. But without going deeper, numexpr allow to use also this technique called OpenMP. It is more advanced technique involving C and Fortran compilers. How we use it in numexpr? So first we need to do the usual pip install numexpr, and then when we write the code, we just do the usual import. So we import numexpr, and in particular in this case the evaluate command. The usage of numexpr is very simple. We just rewrite the expression as a string with the reference to the local variable. Write the expression that we want to evaluate as a string. So you see here that this is a string. In this case, we use the out parameter here of the evaluated function, so the numexpr doesn't allocate a new vector to which to return results of the calculation. If you're looking at the perf results using the numexpr in this case, we see a few more things. So one important thing is really numexpr is very good in dealing with utilization of CPU caches. And here, for instance, we saw that the cache misses are 5.513%. So that's quite amazing results. It does even further specialization on the caches is specifically moves data around to the various CPU caches, so they have the correct data in order to minimize the cache data. So it's considered different caches. Some are also shared by the cores. And when we run the perf, we can actually see here that the cache misses goes quite a lot down. What are advantages and disadvantages of numexpr? Well, the first advantage is coming from the fact, as I told you, that numexpr is actually compiling. So it's compiling the vector operation that we encoded as a string, and this compilation has quite a little bit of overhead. So this overhead need to be absorbed by our application. So what it means absorb? It means that it need to be small compared to the total execution of the code. When the total runtime of the program is small, this overhead can be quite noticeable. So we need some quite long computation to hide the cost of this compilation. Of course, as we increase the grid size in our diffusion problem code, we should expect that numexpr utilize our cache better than native NumPy does. In addition, numexpr utilize multiple cores to do its calculation. We saw also that some numexpress implementation also use OpenMP and tries to saturate all the cores caches. When the size of the grid is small, the extra overhead of managing the multiple cores overwhelm any possible increase in speed. So numexpr is not very good when the problem size is small. Right, so when everything is fitting on the data, our data structure fits into caches, then numexpr is not the best. It's very good in using caches when our data is not fitting into the caches. So let's see a table that is summarizing the different implementation results of diffusion problem codes. So we saw the list implementation, we saw the NumPy, we also saw the in-place implementation. And in this particular lecture, we look at the usage of NumPy plus numexpr. So we focus on these last two rows of this table and the speed up. So the higher in this case is better. So we see here that the implementation I presented in the previous lecture, the NumPy plus in place without numexpr, is the highest, right? So this is speed up, so the higher is better. So the NumPy for small grids is better. However, NumPy plus numexpr implementation results much better for larger grid, and we see that as the grid implementation is increased, also we get very good results. So why is that? And can we actually calculate when this is happening on our machine? So the tests that I presented in the previous slides are done on Intel CPU with 8000 kilobyte L1 cache. Remember that whenever we do a simulation, we need to understand how big, what is the capacity, what is the hierarchy of our memory system. So we need to check first the system that we're using, what is the size of L1. Also, our problem size, we are basically operating on two arrays, one for the input and one for the output. The number of the grid elements can be stored in caches. This is, we need 64 bit, right? So we can store in total on the L1 cache 1 million elements. Since we have two grids, one for the input and one for the output, we divide this number by 2. So we can, in this case, store two grids. Each of these two grids can have 502 elements. Because these two grids are two-dimensional, we want to understand what is the grid size in one-dimensional. So the operation we are doing, we take the square root of this number here. That is the total number of elements for one grid. And we have two grids. If you take the square root and then we see that this number is 715. So approximately a 2D arrays of size 715 by 715 can fit in the cache. Remember that we need the two of these two grids. However, we typically also have other data, not just the two grids, so we can be a little bit more conservative in this estimate. So we can realistically fit two grids of 640 by 640 elements on the grid. So looking at the previous slides, we see that the grids improves here from better performance within numexpr exactly on this part here. So this part is when our data is not fitting anymore on the cache. In this regime, the numexpr is better. In this regime, where we can use the caches, we have no benefit in use numexpr. To summarize the results of this lecture, numexpr is a module that can take an entire vector expression as a string and compile it to efficient code that is optimized to minimize cache misses and temporary space use, so to allow the in-place operation. The compilation of numexpr add an overhead, so we should use it when the total execution of our code is larger compared to this compilation time. Finally, numexpr is better than flat NumPy when the cache reusage is good when the data does not fit into the cache, right? So for instance, the smaller grid is good without numexpr, but the larger grid get a good benefit on using numexpr. This is the last slides of the lecture, and talk to you soon.